everyone, this is Babitha, working as Assistant Professor in the Department of ECE at Institute of Aeronautical Engineering. In this session, I am going to explain about Hartley Oscillator as well as Colpitts Oscillator. So while coming to the contents, just I'll revise what is meant by oscillator and what is the basic working principle required in order to operate the oscillator and Hartley Oscillator as well as Colpitts Oscillator. So while coming to the oscillator, I have already mentioned when we add for the amplifier circuit positive feedback, then it will become the oscillator circuit and it will produce the waveforms. So for the oscillator, we are not providing any input signal. What is the supply voltage we are providing for the oscillator? By using the supply voltage only, it is providing the output signal in the form of different waveforms. That may be sinusoidal waveform or non-sinusoidal waveform. Okay, why we are preferring only the positive feedback here means the positive feedback is going to utilize for generating the waveforms here. Though it is having so many disadvantages, but it is providing the waveforms. That particular waveforms are required in order to test any particular circuit or device in the case of electronic circuits as well as in the devices. Okay, so if we take the normal amplifier circuit, this is the normal amplifier circuit. For the normal amplifier circuit, when we provide the input voltage, we will get the corresponding amplified output voltage with the gain A, or we can write it as A. So across the output, we will get the gain into output voltage. Okay, so if we write the gain of this particular amplifier, we will get it as the ratio of output voltage by input voltage only. This is in the case of normal amplifier circuit. But when we talk about the oscillator circuit, in the case of oscillator circuit, we have to take some portion of the output voltage and we have to giving to the feedback circuit. So the output generating from that feedback circuit, again we are giving back to the input of the amplifier. So that one we are showing here. This is the amplifier circuit and this is the feedback network. So in order to take some portion of the output voltage, we are utilizing the sampling process here. So by using the sampling process, we can take some portion of the output signal here. So that signal may be either voltage or current here. And so some portion of the output voltage, so that's why we are indicating with the V0. So V0 is the input for this feedback network and the output for this feedback network is VF, that is the feedback signal. Okay. So again this feedback signal we are giving back to the input by using mixer here. By using the mixer circuit, we are giving both the applied voltage as well as the feedback voltage. So this one if you make it as Vs and if you make it as Vin. So in this particular case, Vin is the sum of Vs plus Vf. Why? Because it is positive feedback. So that's why we are indicating with the plus. If it is negative feedback means we have to indicate it as minus. But in the oscillator always, most of the cases we are going to utilize the positive feedback only. So that's why input voltage, overall input voltage is the sum of the supply voltage plus feedback voltage. Okay. So here, if we take the gain by considering the feedback also into the consideration, for that purpose I am writing the output voltage of the feedback amplifier or oscillator circuit here. So that is V0 equal to gain into sum of both the voltages Vin plus Vf here. So in this case, if we multiply it with gain A, we will get it as A into Vin plus A into Vf. So V0 is the AVin plus, here what is the value of Vf here? Beta V0. How we got this beta V0 means from this feedback network. So here beta is nothing but feedback ratio. Beta is nothing but feedback ratio, and that value we can calculate here it as the ratio of feedback signal to the V0 signal, that is nothing but output voltage to the input voltage. Output voltage for the feedback network is Vf, input voltage for the feedback network is V0. So that's why it is Vf by V0. So from this we can write it as feedback voltage as multiplication of beta and V0. So that's why in the place of Vf we replaced it as beta V0. So take this term into the left side. If we take this term into the left side means what we will get? V0 minus A beta V0 is equal to A into V. And take V0 common here, that is 1 minus A beta is equal to A into V. So from this we can write the ratio of output voltage by input voltage is equal to A by 1 minus A beta, where A beta is nothing but the open loop gain here. So to get the sustained oscillations, we have to maintain always A beta value as 1 whenever the input signal is 0. Why input signal is 0 means in the case of oscillator, we are not at all providing any external AC signal here. By using the supply voltage itself, it is converting the DC signal into the AC form. That may be the sinusoidal nature or maybe the non-sinusoidal nature. Okay. So what is meant by sustained oscillations here? Sustained oscillations means across the output of the oscillator, we need to get the constant amplitude signal with the stable frequency range. That is nothing but amplitude as well as frequency range of the signal should not change, so that we can say these oscillations or these waveforms are called sustained oscillations or sustained waveforms. So in order to design any oscillator circuit, here we have one criteria, that is the Barkasian criteria. Barkasian is a scientist. He invented two conditions to design any particular oscillator circuit, that is the magnitude of open loop gain always must be equal to 1 for any oscillator circuit. So here in the open loop gain, we are considering both the gain of the amplifier circuit as well as the feedback ratio of the feedback network. So the multiplication of that gain as well as the feedback ratio is the open loop gain. So that open loop gain magnitude must be 1 and the phase angle of that open loop gain must be always 0 degrees or 360 degrees. So to design any particular oscillator, that may be the Hartley oscillator or Colpitts oscillator or RC phase shift oscillator, any kind of oscillator, we need to satisfy these two conditions here. So this value we have already derived. We got it as A by 1 minus A beta. So I have already mentioned, if we maintain A beta value as 1 only, we will get the stable signal. There is nothing but this particular signal we can expect when open loop gain value is 1. So if we observe this particular waveform, the amplitude in the positive direction and the amplitude in the negative direction both are same and in constant range, and the frequency value also not changing here. But if this A beta value is greater than 1, suppose if we maintain this value as greater than 1 means we will get it as overdamped oscillations. Overdamped oscillations, that is nothing but how much frequency if we are increasing, along with that frequency the amplitude of the signal will increasing here. Okay, the amplitude of the signal is increasing here in the case of overdamped oscillations. That we can achieve whenever we maintain the open loop gain value as greater than 1. Okay, suppose if our open loop gain value is less than 1, in that case we will get underdamped oscillations. So in this case, what will happen? The amplitude of the output voltage is decreasing towards the horizon here, as well as frequency also varying here. So this particular signal is undamped signal without any variations here. So always we prefer this particular undamped oscillations only from any kind of oscillator network. So our next type of oscillators are the LC oscillators. So what is mean by LC oscillator here? If we design any oscillator circuit by using the inductor as well as capacitor, so that we can call it as LC oscillators. So if we construct the circuit using inductor and capacitor elements, so that we can call it as tank circuit, that particular circuit we can call it as tank circuit or oscillator circuit. Okay. So before going to the types of LC oscillators, how this tank circuit is utilizing in order to generate the oscillations in the oscillator network. So for that purpose, I am considering one capacitor as well as one inductor. So the parallel combination of both the capacitor and inductor I am considering here. So in that first I am considering the capacitor only. I am considering only capacitor. So for this capacitor I am providing some DC supply with positive and negative polarities. So when we apply the DC source to this capacitor, the capacitor starts charging here. So in this particular plate of capacitor, the positive charge is storing, as well as in this particular plate of capacitor, the negative charge is storing here. So depends upon the which type of polarity of source we are applying for the capacitor. According to that, the capacitor starts charging here. So for this particular charged capacitor, okay, I am connecting parallelly one inductor circuit. So now capacitor is with fully charged. So once we connected this fully charged capacitor parallel with this inductor L, so now the capacitor starts discharging through this inductor here. So in this direction, the current will flow in the circuit in this direction, and the capacitor will start discharging through this inductor. So once the capacitor starts discharging, means the inductor acquires the magnetic field here. Why? Because in the case of capacitor, the energy stored in the form of electrostatic field. So once it is discharging, means the energy is accumulated across the inductor in the form of magnetic field. So once the capacitor is discharged totally with the total applied voltage is discharged here, means now the inductor is fully charged with the magnetic field here. So now again, what will happen means I am taking same circuit. Okay. So according to Lenz's law, this magnetic field is accumulated across the inductor, and according to Lenz's law, it's slowly disappearing. This magnetic field will slowly disappearing here. So once it is starting disappearing, means the capacitor starts charging here. Okay, the capacitor will start charging with the opposite polarity here. The capacitor again starts charging with the opposite polarity here. So here it is positive charge, here it is negative charge. And after totally charging the capacitor, again it will discharge through the inductor here. So from this particular condition, we'll get the positive cycle of the signal, and for this particular condition we will get the negative half cycle of the signal. So always the energy is changing from capacitor to inductor, and again from inductor to capacitor, that is from electrostatic to magnetic field and magnetic field to electric field. So because of that energy conversion, there is a occurrence of the signal across the tank circuit or across the oscillator circuit. So which type of oscillations we can expect from this particular tank circuit is underdamped oscillations in this way. So in the case of underdamped oscillations, the amplitude of the signal is decreasing here. So these kind of signals we will get from the LC tank circuit oscillators. But in order to operate our oscillator as a perfect one, we have to make it as AB value as or A beta value as always 1. But in this case it is not achieving that value. We are getting here it as A beta value as less than 1. So that's why we are getting the underdamped oscillations here. So at what frequency this particular circuit is generating this oscillation means F equal to 1 by 2 pi under root of LC. So with this particular frequency, the signal is generating across the oscillator circuit or LC tank circuit here. So by using this particular concept only, we are going to design the LC oscillator circuits. So this is the basic concept required for the LC oscillator circuits. So in the case of, I have already mentioned, in the case of LC oscillator circuit, when we combine the LNC components are used to get the sustained oscillation, so that we can call it as the LC oscillators. Actually, why we are moving for this LC oscillators, even though we are having the RC phase shift oscillator as well as the Wien bridge oscillator here. See, in the case of RC phase shift oscillators, those can able to generate the signals from 20 Hz to 20 kHz range of signals only. Okay, but if you wanted to generate the high frequency signals, so that we can able to move for the LC oscillator circuit. Okay, so for greater than 10 kHz or almost we can say some 200 Hz, 200 kHz and above signals from the LC oscillators. Okay, so how we can develop this LC circuit means by using the tank circuit formed by inductor and capacitor. Just now we have discussed about that. Okay, so here in the case of LC oscillator, for any oscillator we are having the amplifier as well as feedback network. So here this is the amplifier circuit and this one is the feedback circuit. And this is the feedback circuit. Okay, so in this case this amplifier is used to generate 180 degrees phase shift, as well as feedback network is also used to introduce 180 degrees phase shift. So the overall phase shift is either 360 degrees or we can also call it as 0 degrees. So in the case of LC oscillators, we are having in the feedback network, we are having 3 impedances. So in these 3 impedances, we can replace here it as either inductors or capacitors to make the LC oscillators here. So that we'll see in the later slides. So in the case of LC oscillators or high frequency oscillators, we are having 4 categories. Those are Hartley Oscillator, Colpitts Oscillator, Clap Oscillator as well as Crystal Oscillator. So now we are going to discuss about Hartley Oscillator. So before going to the Hartley Oscillator, first of all, how to design the LC oscillator we will see now. So this is the general structure of the oscillator circuit, consists of amplifier as well as feedback network. And the output voltage of this oscillator will take across the impedance Z2 here, and the feedback signal we will take across the Z1 impedance here. And in this case, the amplifier we have to choose in such a way that it should provide the maximum gain as well as 180 degrees phase shift. Here in this case we can utilize to get it as bipolar junction transistor or field effect transistor or operational amplifier. We can utilize any one of these devices to construct the amplifier in the case of oscillator. And anyways, in the feedback networks we can utilize either inductors or capacitors to form the tank circuit and to generate the sustained oscillations with the desired frequency. Okay. So in order to analyze this particular LC oscillator circuit, I replaced the amplifier circuit with its hybrid model here. So that amplifier block, I am replacing it with the hybrid equivalent circuit. Generally, in the case of hybrid equivalent circuit, we are having the HIE component, HRE VCE element, and HFE IV, and 1 by HOE. And here we will apply the input signal and voltage. So this is the hybrid equivalent circuit of the amplifier circuit in the exact model. In the exact model, we will consider all the 4 H parameters here. Okay, HIE, HRE, HFEI, HOE. All the H parameters we will consider in the exact model of the hybrid equivalent circuit. But in order to simplify the analysis process, instead of taking this exact model, we are going for the approximate model here. So in the case of approximate model, we are neglecting the HRE as well as HOE terms. Why? Because this HRE term, that the drop provided by this HRE voltage is very less compared to the overall input current here. So that's why we can neglect this. And similarly, if we compare the output admittance, this output admittance value is very less compared to the output impedance provided from the circuit. So that's why we are neglecting HOE also. So after neglecting this HRE VCE as well as this 1 by HOE, we will get it as only HIE and HFE into IB. So this same circuit only we are utilizing here. This is HIE, and HFE IB. That is nothing but we are utilizing the approximate model of the hybrid circuit in order to simplify the analysis. And in the case of feedback circuit, we are taking here it as it is. So to find the frequency of oscillations or overall LC oscillator equation, I am finding the overall impedance of the circuit. So the overall impedance I am taking here it as ZL, load impedance, and that we can calculate here it as this Z1 is the input impedance and it is parallel to the input impedance of the amplifier. Here Z1 belongs to the feedback network and HIE belongs to the amplifier circuit, and these two are in parallel. So that's why we are writing here it as Z1 parallel with HIE, and plus again we are having these two impedances are in parallel. Why? Because in between these two impedances we are made it as ground. So that's why these two are in parallel now. So I'm very sorry. These two are Z1 parallel with HIE here plus this particular Z3. So this overall impedance is parallel with Z2 here. So here ZL value is this much. Here Z1 parallel with HIE, we can write it as Z1 into HIE by Z1 plus HI. Okay. So this value I have written here plus Z3. So again these two are in parallel. So we can write it as Z1 HIE plus Z3. So take LCM here, that is Z1 HIE plus Z3 into Z1 plus HIE divided by Z1 plus HIE parallel with Z2. Again these two are in parallel now. So if you write it as this total term into Z2 divided by this total term plus Z2. So if we simplify this, these two terms will get cancelled, and after taking the LCM, we will get the simplified expression as Z1 HIE plus Z3 into Z1 plus HIE into Z2 divided by this term Z1 HIE plus Z3 into Z1 plus HIE plus Z2 of Z1 plus HIE. So this is the load impedance or overall impedance of the LC oscillator circuit. So in order to design the oscillator circuit, what we require? Gain value as well as feedback ratio value. So in order to find this gain value, we require the ZL. So that's why we have calculated the ZL value in the previous slide. Okay, and next we need to find the feedback ratio beta here. Okay, so ZL value, we got this much. So by using this, if we write the gain of the common emitter amplifier is, that is HFE by HIE into ZL. That is from the circuit only we are writing here. See, this HFE divided by HIE into overall impedance, that is ZL. This is from only amplifier circuit. That's why we are taking only hybrid parameters here. We are not including any other parameters minus HFE into HI into overall impedance ZL. Okay, and now to calculate the VF value, beta value. Beta is nothing but what VF by V naught. So to find the beta value, we require VF value first. So that's why I am calculating the VF value here. So how we can calculate the VF value? Actually, where this VF value is appearing in the circuit, see, this VF value is we are taking across the Z1 impedance. So that's why I am taking only that particular part here, HIE, Z1 and Z3 V naught. So to find VF, we have to apply the voltage division rule here. That is VF equal to opposite voltage, that is V naught into opposite impedance or opposite resistance is what? Z1 parallel with HI. So that's why Z1 parallel with HI divided by Z1 parallel with HI plus this particular impedance. Okay, voltage division rule, opposite voltage into opposite resistance by overall resistance. So this one we can write it as Z1 into HI by Z1 plus HI, as well as in the denominator also C. So here we can write it as Z1 HIE divided by Z1 plus HIE whole divided by Z1 HIE plus Z3 of Z1 plus HIE divided by Z1 plus HI. So these two will get cancelled, so that we will get it as Z1 HIE by Z1 HIE plus Z3 of Z1 into HI. So this is the feedback ratio. So VF by V naught. So now we got both the values. We have the value of AB as well as beta. So to find the value of A beta, substitute the values of gain as well as feedback ratio in this expression to find the frequency of oscillation. So according to the Markson criteria, to generate the oscillations from any oscillator circuit, we have to maintain the magnitude of the open loop gain must be greater than or equal to 1. So whether it is satisfying that particular condition or not, we have to substitute the gain as well as feedback ratio here. So the gain value is minus HFE by HIE into ZL. So that's why I have written here it as minus HFE by HAE, and this value is the ZL value here. Okay. And what is the beta value? Beta equal to, just now we have calculated this much. So the same value I am considering again here. So now substitute these AB and beta in this equation 1. So this one is as it is into this beta value. So here what will happen? This HIE and this HIE will get cancelled here. Okay. And okay, if we here in the numerator we will get Z1 HIE plus Z3 Z1 plus Z3 HIE overall multiplied with Z2. So this term here it is. Oh, here if you compare these two, these terms will get cancelled here. Z1 HIE plus Z3 Z1 HIE will get cancelled here as well as here. So the remaining terms minus HFE into this Z1. Okay. Sorry, this one is get cancelled already. This Z1 into Z2. Okay, minus HFE Z1 into Z2 divided by denominator is as it is here. This much is equal to 1 here. Okay, so if you cross multiply here, this total term is multiplied with 1 and this is equal to 0 minus this is equal to, if you write it as plus HFE Z1 Z2. Okay. Actually after cross multiplication we will get it as minus HFE Z1 Z2. If you take into the left side we will get it as plus HFE Z1 into Z2 equal to 0. And here see the HIE terms. HIE here, here as well as here. So take HIE common here. If we take the HIE common, HIE of Z1 plus Z2 plus Z3 plus this Z1 Z2 as it is and this Z1 Z3 as it is and this HFE Z1 Z2 also as it is. And again see the Z1 Z2 terms. See Z1 Z2 term is there here as well as here. So take Z1 Z2 common here. If you take Z1 Z2 common we will get it as 1 plus HFE into Z1 Z2 plus this value as well as this value. So this is the overall expression for the LC oscillator circuit. So in order to design any kind of LC oscillator circuit, this one we have to take it as the base equation. So in this base equation only we have to include the inductance values. Why? Because for the different oscillator circuits we will get different impedances here. That is nothing but we will get either inductance values or capacitance values here. So in that LC oscillators, first type is the Hartley Oscillator circuit using BJT I am considering here. We can also design by using the field effect transistor or also by using the operational amplifier. So if we see the first basic circuit of this LC oscillator, what we are having here amplifier as well as the feedback network. So this amplifier we are replacing with the BJT amplifier, and in the Hartley oscillator this Z1 is inductance and Z2 is also inductance and Z3 is capacitance. That is nothing but 2 inductors and 1 capacitor. So that's why here it is Z1, Z2, Z3 we replaced with 2 inductances and 1 capacitor. Here we are taking 2 combinations. In one place 2 Z1, Z2 are inductors and Z3 is capacitor is one combination. In that case we can make it as the Hartley oscillator. Or else if we can take 2 capacitors here and 1 inductor here, means that will becomes the Colpitts oscillator. That is the another kind of the oscillator. That is nothing but we are trying to design the different feedback circuit in order to generate the different variations in the waveforms. So here while coming to the amplifier circuit, Though it is the common emitter amplifier, it will introduce the 180 degrees phase shift. And here for this circuit, this R1, R2 resistances are used to provide the required biasing for the transistor, and also they will operate the transistor in the active region, and they'll maintain the proper operating point in order to get the stabilized signal. And across the collector, we will take the output here, that is V0. So this output through the coupling capacitor CC, again we are connecting to the feedback network here. Okay, the output of this amplifier through the coupling capacitor CC, we are connecting to the feedback network. So here, this one is our feedback network. Okay, and C is the common emitter capacitor, which is used to bypass the any noise signals which are present in the circuit. Okay, so the function of the feedback network is to again introduce the 180 degrees phase shift, and it acts like a tank circuit. Again, why? Because it is the combination of both the inductors as well as the capacitors. So because of the transformation of electrostatic energy into the magnetic field energy, or from magnetic energy to the electrostatic energy in these inductors and capacitors, there is a variation in the positive amplitude as well as the negative amplitude, so that we will get the signal in both the directions. So while coming to the analysis of this Hartley oscillator, so we are taking the general equation of the LC oscillator. Just now we have calculated this one, 1 plus HFE into this total thing. Again I am considering here. Okay, so in this equation, in this case, Z1 is nothing but L1, Z2 is nothing but L2, and Z3 is nothing but C here. So the same thing I am taking here. Z1 is nothing but L1, Z2 is nothing but L2, Z3 is nothing but C. So we are indicating in terms of reactance here. So the reactance of the inductor is J omega L1. So here reactance of the second inductance is J omega L2, and the reactance of the capacitor is 1 by J omega C, or else we can also write it as minus J omega C here. So now substitute this Z1, Z2, Z3 in the first equation. So wherever Z1, Z2, Z3s are there, we have to substitute these values. So after substituting these values, we will get it as this much. So here I am taking this J to the numerator, so that's why this plus will become minus here. This remaining total equation is as it is. Okay, so in order to find the frequency of oscillations or at resonant frequency, the imaginary part of this particular equation must be equal to 0, or else to find the frequency of oscillations, the imaginary terms must be equal to 0. So that's why I am taking only the imaginary terms here, that is HI into L1 plus L2 minus 1 by omega C is equal to 0. So in this case, what I am doing here, it is this omega L1 plus L2 minus 1 by omega C is equal to 0. So this HI I have taken to the right side. And next again I am taking omega L1 plus L2 is equal to 1 by omega C. And next I can write it as L1 plus L2 equal to 1 by omega square C. This is this. We are taking this one into the right side. So again we can write it as the value of omega is equal to 1 by under root of L1 plus L2 into this capacitor here. So here omega value is 2 pi f. So that's why from this we can write f equal to omega by 2 pi. So that's why omega is 1 by root of L1 plus L2 into C, and it is 1 by 2 pi. So that's why 1 by 2 pi of under root of L1 plus L2 into C. So by including the mutual inductance, if you include the mutual inductance also into the consideration, we will add the 2m here. So the frequency of oscillations in the case of Hartley oscillator is 1 by 2 pi under root of L1 plus L2 plus 2m into C. So general frequency of oscillation is 1 by 2 pi under root of LC. Here in this case only LC. Why? Because it is for the general tank circuit. In that we are taking only one inductor and one capacitor. So that's why under root LC. But in the Hartley oscillator we are taking two inductors and one capacitor. So that's why the equation also included two inductances. And to find the gain again I am taking the real part of the general equation. So this is the general equation. In this case I am taking the real part. This is the imaginary part. We have utilized it to find the frequency of oscillation, and this is we are utilizing to find the gain of the amplifier. How much gain required from that oscillator. Okay. This is the real term we are taking. Okay. So this term we are taking into the right side. So we will get it as minus will get cancelled. You will get it as L1 by C, and here omega value is 1 by under root of L1 plus L2 into C. Just now we have calculated. So if we substitute that here, we will get it as 1 plus HF equal to L1 by L2 plus 1. And take this one right side, means we will get it as 0. So HF equal to L1 by L2. And again if we add the mutual inductance for both the inductors, we will get it as the gain or feedback gain is L1 plus M by L2 plus M. So in order to create or generate any kind of oscillator, that may be the Hartley oscillator or Colpitts oscillator, we have to satisfy the frequency condition as well as gain condition. In the case of Hartley oscillator, frequency we got it as this much, and the gain we are getting here it as this much. So for any oscillator we have to derive these two parameters, gain as well as the frequency of oscillation. That is nothing but how much gain the amplifier of the oscillator is providing, and the frequency of the oscillation indicates at what frequency range the waveform is generating from that oscillator circuit. And next type of oscillator is the Colpitts oscillator here. So what is the basic difference between the Hartley oscillator as well as the Colpitts oscillator is, in the case of Hartley oscillator, here it is Z1, Z2 and Z3. In the case of Hartley oscillator, Z1 equal to L1 and Z2 equal to L2 and Z3 equal to C we have taken. But in this case, Z1 equal to C1, Z2 equal to C2 and Z3 equal to inductance. That is nothing but instead of two inductors we are taking two capacitors, and instead of one capacitor we are taking one inductor here. So this amplifier circuit is as it is here, that will provide the 180 degrees phase shift with the gain. Okay, this R1, R2 resistances again are used to provide the biasing for this transistor here. Okay, and those will also operate the transistor in the active region and to achieve the proper operating point, and it will provide the stabilized output. So what is the output we are getting from here, or VC, through the coupling capacitor? It is connected to the feedback network again. So in this case, this is the amplifier circuit, and this one is the feedback network. So that's why the output of amplifier is connected to the feedback network, and again the feedback is connected back to the input of the amplifier through the again coupling capacitor here. So the function of the feedback network in this case also to generate the 180 degrees phase shift. So that's why we need to satisfy the Barkasian criteria to reach the total 360 degrees phase shift, 180 from the amplifier, 180 from the feedback network. So in this case also we need to find the frequency of oscillation as well as gain of the oscillator. So for that again I am considering the general equation of the LC oscillator, we derived in the previous slides. So this is the general equation of the LC oscillator. So in this case, Z1 equal to C1, Z2 equal to C2, Z3 equal to N. So the reactance of the capacitor is 1 by j omega C1, and here it is 1 by j omega C2, and the reactance of the inductor is j omega L. So now substitute all these Z1, Z2, Z3 values in the equation 1, so that we will get this one. Again, to find the frequency of oscillations, we have to take the imaginary part to find the frequency of oscillations. And to find the gain of the amplifier, we have to take the real part of this equation. So first I am taking the imaginary part of this equation to find the frequency of oscillations. So that imaginary part must be equal to 0 at resonant frequency. So here I am taking L minus, from this equation, L minus 1 by omega square C2 minus 1 by omega square C1 is equal to 0 here. J omega. So this HI will get cancelled here. So from this I am writing this total term will also 0 here, and from this we can write L equal to 1 by omega square C2 plus 1 by omega square C2, C1 C2. That is this particular equation. So from this I am taking omega square in the denominator terms, and I took into the left side. So omega square L equal to 1 by C1 plus 1 by C2. So I am letting here this overall 1 by C1 plus 1 by C2 as the 1 by C equivalent. If we take in that way, omega square L equal to 1 by C equivalent, or else we can write it as omega square equal to 1 by LC equivalent, and omega equal to 1 by under root of LC equivalent. And what is the value of omega? That is 2 pi f. So from this f equal to omega by 2 pi. So that's why here it is 1 by 2 pi under root of LC, omega by 2 pi. So this is the frequency of oscillation for the Colpitts oscillator. And similarly, to find the gain provided from this oscillator, we have to consider the real part, this particular real part. So I am taking that real part, I am equating it to 0. So from this we can write it as L equal to 1 plus HFE into 1 by omega square C square. C2. This C1 will get cancelled if you take into the right side. So 1 plus HFE equal to L omega square into C2 after cross multiplication, and 1 plus HFE equal to L into omega equal to, in this case, 1 by L into 1 by C1 plus 1 by C1. Why? Because 1 inductor, 2 capacitors. So substitute that omega value here. It is under root, so this square will cancel with this under root. So that's why L into 1 by L into this total value into this capacitance C2. So 1 plus HFE is equal to 1 plus C2 by C1. After simplification, from this we will get it as 1 plus C2 by C1. So this one will get cancelled. So HFE is equal to C2 by C1. So the feedback gain or gain provided from the Colpitts oscillator is the ratio of two capacitances C2 by C1 here. And in both the cases, feedback voltage we will take across this capacitor, and the output voltage we will take across this capacitor. That may be in the Hartley oscillator or in the Colpitts oscillator. So in this session, we have seen the what is meant by LC tank circuit, and what are how the oscillations are generated from the LC tank circuit. And also we have seen the Hartley oscillator, how the Hartley oscillator is forming, and what is the analysis for Hartley oscillator, and also the Colpitts oscillator construction, as well as working principle and the frequency of oscillation and gain of that Colpitts oscillators. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.